module of today. It's the Astrophysics and Cosmology module. Yes?
Be a co-host while you're talking. I can help you.
Yes, please. Yes, please. Let me just, I should have done that immediately. Okay, you are co-host. So you can admit people. I don't have to keep looking at it. So today, I'm going to be here. I'm Luisa Almeida from NUCLIO. My background is physics and then astrophysics, well, more astronomy, observational astronomy. And from NUCLIO, we have Rosa Doran. You can present yourself, although I think everybody knows you, Rosa.
Not everyone. So I'm Rosa Doran. I'm an astrophysicist by training. I used to study black holes, but together with Maria Luisa, we created a nonprofit and NGO for development called NUCLIO. And we started doing science education and outreach, and here we are. So this is, in a very brief nutshell, a bunch of astrophysicists doing astronomy and science education all over the world, which is a privilege. And this is my favorite place to be. It's among teachers. It's where I feel more useful and comfortable. So it's very good to be here.
I still don't see Joanne here, but if she doesn't join us this morning, she will join the group because she has been working with us in this module. She's a teacher and she has had some opportunity to look at the demonstrators, and she has already done an activity with for the students based on the demonstrator, on one of the demonstrators. So she will be very helpful to guide us how to transform demonstrators in other activities. And finally, we have Giulia. I think I've seen Giulia here.
Hi, yes.
Yes, can you introduce yourself, please?
Yes, of course. So I'm Giulia Vannoni. I'm also an astrophysicist by education. So I'm Italian, so I studied in the University of Florence. I studied physics, and then I moved on for my PhD to the Max Planck Institute for Nuclear Physics in Heidelberg, Germany, where I worked basically on the acceleration and radiation of cosmic rays. And then I moved to France and changed career as well. So at present, I am the project manager of the Paris Center for Cosmological Physics, which is a structure inside the Astroparticle and Cosmology Laboratory of the University of Paris. And we are one of the partners of the Frontiers project.
Thank you, Giulia. So I think we are ready to go. Let me take this from. So today we're going to focus on the demonstrators of this module. We can divide the demonstrators on a few topics. I have written down the topics that we will explore. We have the exoplanets, the black holes, the age of the universe, and the sun. So there are demonstrators that focus these topics. Of course, you won't be able to know everything about each of these topics, but there are activities that you can take to your students that will help them understand a little bit how research is done in each of these topics. They are demonstrators thought to be done with the students for quite some time, so they are in longer activities. We do not expect that every teacher can have that time in the classroom to apply these demonstrators. Maybe some teachers have astronomy club or science clubs, and then that's okay. But if the teachers have a reduced time to do different things with the students, we would like you to look at the demonstrators. This is, I'm talking specifically to the group that we will follow in this module. We would like you to understand the demonstrator as a whole. So what we are researching within the demonstrator, and then think about an activity that you could do with your students. So adapt it to something that you could take to the classroom. So don't be afraid that they are a little bit big, these demonstrators. The idea is that you can think about an activity based on them that then you can take to the classroom and even adapt to the level of your students. Some of these demonstrators are more evident for 16 to 18 years old, but maybe you're teaching 13 to 15 or even primary schools. So from what you understand of the whole demonstrator, maybe you can think of an activity that is there that you can adapt to your level. I'll stop sharing this and I'll go to the first demonstrator, which will be the one about the exoplanets. So I think I have all of them open here. And I'm at the Frontiers project page, which you probably have already seen. And I went to the menu and chose the demonstrators. And then I chose the Discovering Alien Worlds. As you probably have already explored some of this, but I'll just go through so that I'm sure that everyone knows where the demonstrators are and what you can see that we have prepared for you. So when you click in the demonstrator, when you're in the Frontiers project site, you get a summary of the demonstrator. And this is quite useful since there are so many demonstrators that you can have an overview of what we want with the demonstrator. So first of all, you can see that there's an age group that we were thinking of when we thought about the demonstrator. We have a summary over here that gives you an idea of what the demonstrator will do. And then we have specific information, for instance, the learning outcomes, the prior knowledge, the concepts introduced, and the learning intentions, and the key activities of the demonstrator. So in this case, the summary will tell you that we are going to see how exoplanets are discovered with a certain method, and that method is the transit method, that we are going to use real images. The students are going to learn how to build a light curve, understand how we can analyze it, and in the end, they can take some parameters of a transiting body and reflect if it could be an exoplanet that is transiting a certain star. At the end of the activity, we suggest that they present and discuss their work with the rest of the class. So what do we really want with this demonstrator? We want to teach students about the discovery of exoplanets, allow them to understand the science and methodology behind the discovery of exoplanets, and introduce basic concepts of astronomy and image processing. So for us, it is very important that this is real research. They have real images, and they are going to do exactly like researchers do. There is not a big deal that they have to know before going into this activity. So basic astronomy is enough. The demonstrator should introduce them to what are exoplanets, what is luminosity, how to create a graph that is a light curve. And by the end of this demonstrator, we expect the students to be able to define an exoplanet, explain the transit method, describe a method to collect the luminosity of the stars, examine images using the SalsaJ software, and form conclusions about a planet from a light graph, so a light curve. This is important because here you can see exactly what the students are going to do. So the activities that we are going to put the students through are, they will be watching videos so that they get engaged in the subject. They will need an activity to understand what is a light curve and practical information. They will use SalsaJ to examine, in this case, they will do photometry of 3 stars. Then they have activity that they have to analyze their data and explain. And in the end, they have a final report. So this is what we suggest for this demonstrator. So let me come up here, which is not very evident in the first day. Someone was asking where we get to the demonstrator. Over here, we have the link to the demonstrator in English. There will be other languages added here very, very soon. But at this time, let's go and see the demonstrator. So this is about exoplanets. So the first thing we should do is explain what are exoplanets. We try to do that in an interesting way. We give them information. We try to relate to things that they know from their daily lives. In this case, they know the solar system. So we start by introducing them to a short video of Stephen Hawking explaining the formation of the solar system so that they get engaged in the subject. And then we go on to the curiosity of humankind. This is a question that we have made for so long. Are we alone? Are there other worlds like ours? And how we finally discovered the first exoplanet around a star like our sun. And we have a short video talking about the Nobel Prize of Physics so that they can also understand that what they are learning is something that got the Nobel Prize. So this is important science. This is modern science. This is cutting edge science. And they will be able not only to understand, but also to reproduce something like the science that gave the Nobel Prize. And here we try to get them to know a little bit or imagine. It's more a question of emotional linking to the exoplanets. We have here an artist view, and here they can look at the sky, and if they can identify the constellation, they know that there is a star over there that has a planet going around it. And also we give some information about how scientists are looking for exoplanets. And although we have a big number, what we consider a big number of planets orbiting other stars, at this point we have more than 4,000 planets. We see over here that it's still in a very tiny zone of our galaxy, so that they realize how much we already know, but at the same time, how little we still know. And of course, we have to relate a little bit to what comes next. Why are we so interested in exoplanets? It's not just because we want to know the number of exoplanets that there are. The next step is obviously see if there are planets that have life. And so we have here a hint of what now we are looking for in those exoplanets that we are finding more and more. At this point, we can already detect exoplanets that are much more similar to our Earth than at the beginning. And so they should understand that this is very important for us to know exoplanets. If we afterwards can even see if there, or imagine if there is life, if there are conditions for life. And we're back to what we want from the demonstrator. So how do we find exoplanets? Exoplanets cannot be seen directly. The light of the stars don't allow us to see the exoplanet easily. So we had to get different methods to try to detect exoplanets. And we have a short video that explains different ways of detecting exoplanets. And here we are going directly to the method that we are more interested in, which is the transit. So we explain what it is, planet transiting and not transiting a star. And we invite them now to hunt for an exoplanet. So this is the phase. If you remember on the first day, Margaret showed that we have this inquiry phase methodology, and we are in the orienting and asking questions. So this was the first phase that we wanted students to know a little bit about exoplanets and get interested in hunting one. So we would like them to think about how we can detect an exoplanet if the exoplanet is transiting a star. So we have here two GIFs, images. One is a star on its own, and the other one is a star with a transiting planet. And now we ask them, if you are an astronomer and you can measure the brightness of the star, what would you expect in one case and what do you expect in the other case? Should there be differences because there is a transiting body there? And we ask them to discuss with their colleagues and think a little bit if you have a graph of the brightness of the star with time, will it be altered because there is something passing in front? And of course, we over here show, this is for the teachers, whenever in the demonstrators you see this gray rectangle is where we give some information for the teachers. So if the students cannot really understand what we want them to think about, the teacher can also show this GIF. And I think it turns out to be quite obvious that if you can have a graph of brightness with time, if there is a planet transiting, you should see a dip over here. And that is the basis of the model that they have to think about so that they can investigate with real images if they can find a transiting body, in this case, if it is an exoplanet. So more questions for them, as you see in this phase, hypothesis generation and design. We want them to really think about the subject with whatever they already know and with the information that we give them so that they try to make their own hypothesis. In this case, their hypothesis will be that if we have a light curve and we see a dip, we might think that there is a transiting body over there. And now that they are understanding that they need light curves, we can go and plan and investigate in the next phase. So we have told them that it would be useful to measure the brightness, but how can we measure the brightness? This is where they have real hands-on astronomy experience. We have real images. I think they are 20 images, yes, of the same region of the sky. And they were taken with an interval of exactly 14 minutes each. And we are going to ask them to measure the brightness of 3 stars of those images. So that afterwards, since they have the time when they were taken, the images, then they can plot the brightness versus time. To measure the brightness, we're going to introduce them to a software called Salsa J. So this morning, I'm not going to explore here with you the Salsa J because it would take too much time for the purpose of this morning workshop. But afterwards, the group that follows the astrophysics, we will have the opportunity to download and have a practical session for Salsa J. I just want to show you that it is clear, and we believe that with these simple instructions, the students can make the photometry of the stars. So usually what is more problematic is to have Salsa J downloaded and working, but that's something that we will talk afterwards in a practical session. But after having Salsa J installed, the way we can use it, it's very, very easy. So we try to explain to them that if they open Salsa J, they open an image. These are the images. They will look like this. There are 20 of them. They have 3 bright stars, which are the ones we would like them to measure the brightness. Why do we want them to measure the 3? Because 2 of them will not have any special thing in the light curve, and 1 of them will obviously show something different that they can explore if it can be an exoplanet. So instead of only giving 1 star that they would analyze and they would see the dip and go immediately to the conclusion that it could be an exoplanet, we are giving them the chance to see the difference between stars that have something and stars that don't have something. So that's why we are asking them to study those 3 bright stars. So how does the photometry with the CCDs work? Using the Salsa J software or some analogous software, we do what we call aperture photometry. This means that we define a circle where we say that all the light that is within that circle is light that comes from the star. The CCD has in each pixel a number that is proportional to the light that entered that pixel. So if we sum all the pixels in a circle with a certain radius that we define as having the starlight, then we have the brightness of the star. Well, in fact, we still have to subtract the fact that the sky also has some brightness. So what we tell the software to do is to consider a certain radius where the star is, and we give it a way to calculate the brightness of the sky nearby. We could just take a sample, an average, and say that's the sky value, so that we have to multiply by the area that the star occupies and then subtract it. Or like most softwares will do, we define the radius of the star and then we define an annulus around the star, you know, further away from the star where we think the starlight doesn't affect the sky, and it calculates the sky from this annulus, and then it subtracts the value of the sky that contributes to the starlight. And it gives you a number that is proportional to the brightness of that star. And so that's what we explain over here, that we sum the intensity of all the pixels inside the circle of what we consider is a star, and we subtract the sky value times the area of the circle. In fact, we do not do that. It's the software that does that. So what they really have to do is give a radius to the star. In this case, we already give them a suggestion of the radius, because to determine the radius, that would be another exercise. which we can afterwards talk about. But for the purpose of this demonstrator, we give them the radius and the way that the sky value is going to be calculated. So they just have to understand that we are collecting the light that comes from that star. So after we have those parameters, which is the star radius and how to calculate the sky, what they do have to do is tell the software photometry and go to the stars and click at the center of the star. And the software will give you the result. This would be the image, X and Y coordinates of the star, and the star's intensity. And it gives you some information about how it calculated the star's intensity. It is not very important for the students. What they really want to know is for each star, this value, and for each image. So they have 3 stars and they have 20 images. They're going to have 60 values. And after doing that, they are ready to build the light curve. We suggest to use a spreadsheet that we have already prepared, but of course that can be adapted if the teachers want to do something different. But this is a way that the spreadsheet, after having those values, can build immediately the light curves. That is what we are going to see in the next phase, which is the analysis and interpretation. So if they have the values and they plug it in the spreadsheet, they will come out with something like this. What we have here is the light curve of 3 stars normalized. So the spreadsheet is already prepared to normalize the brightness of the stars so that we can see them all over here. And we see that 2 of them have a more linear behavior, but 1 of them really goes down over here. So we can discuss the errors, why there are small differences, although we could fit something more like a straight line over there. But over here, definitely, we have something different. And we asked them to think about, of these 3 curves, which one would you think has a transiting body? So we expect, of course, that they identify, in this case, the star number 1, and they should be able to argue about it. Now that they have a light curve, maybe they can take some parameters from it. And that's the next part. So we have here the light curve with the different position of the transiting body. And we called each of this instant T1, T2, T3, and T4. And we try to guide them so that they can take some information. We don't give the formulas directly. We try to have them thinking when the body is exactly outside with the first contact, and when he is in the second contact, it means that the whole body traveled its diameter. That's what we ask them over here. What happens physically between instants T1 and T2? So this small body has traveled its own diameter. And when it goes from T2 to T4, it travels the whole diameter of the star.
That's
so
only true if it's...
Sorry?
That's only true in a small instance. That's not always true. It doesn't always cut right across the equator.
Yes, we will talk about that afterwards.
Sorry.
We don't want to confuse them. No, but it's a very pertinent question. we could have already said something to the students about that, but I think that it would get too complicated if we started analyzing it right over here. We are going to ask that afterwards, okay?
Thanks.
But it's exactly those kind of questions that we want the students also to have. In this case, so this is like the first approach for the students. We draw something really neat so that we can take those parameters. And so we ask them what would be the ratio between these two different of the times. And that would lead them to understand that they can know the ratio between the diameter of the exoplanet and the star. Afterwards, we give them a value for the diameter of the star, which is in the literature, and they can estimate the diameter of the transiting body. And we still ask them to compare that diameter that they got with the Earth's diameter, so that they can speculate about the nature of the transiting body. Is it like Earth? Is it 100 times the Earth? Is it the diameter of the sun? So that they can get the feeling that it could represent many different things. And at the same time, we have a tricky question, which is the difference between T1 minus T3 and T2 minus T4. So going from this to this would be equal to go from this to this. So this is just for them to think a little bit about what they can extract from the light curve. So now that they have seen the ideal case, we expect them to do that for their own curve. So they should have some values and should discuss between themselves. Did they detect something? Did those parameters that they calculated or estimated, should it be a planet? Could it be some kind of other object? And now here comes the question. Did you take into account that even if it has a transiting body, its orbit might not be edge-on? So how will that affect the parameters you measured? So here is exactly what you were saying. What we know is just a limit to what can be really happening, because not all orbits will be transiting. Yes, please.
How do you manage to get the T1 and T2 times? I mean, it's easy to see when the light is low, so the planet is inside the star, in front of the star, but how do you manage to get from
something like this
position T1?
Okay, so the idea is that this should mimic this. You can do it in a very raw way, which would be to estimate more or less over here T1 and over here T2 and over here T3 and then back here T4. That would be very raw. Or, depending on the age of the students, you could try to model here a curve. And then you could take from the modeled curve. So it depends on how far you want. Sorry?
Do you mean that T1 is the very top of the dip?
Well, it should be somewhere over here. It doesn't really, yes.
And then you think that T2 is the bottom of the dip, the first point at the bottom?
Yes.
Yes, okay, I understand.
So that should be very raw, okay? But for younger students, I think that should be enough because it's just an estimation. But for older students, it would be a nice exercise for them to try to fit the curve.
Okay, thank you.
From our demonstrator, we really don't say anything. It's up to them. So they should choose a way. They should discuss between themselves and they should choose a way. Of course, the teacher can lead them to different ways of doing it. So all these are questions that they have to think about from the analysis they did. And we still have an important one. Are all dips in light curves due to transiting bodies? What else could be happening? How do you distinguish the different situations? This is not a very easy question. I'm not expecting that the students will think of many different things that could be happening. They can also look for, explore somewhere about light curves and what we can take when they are from them when they are not linear. So this is like an extra work that they could do to understand a little bit more about light curves. And we still have here the possibility for them to compare their result with the published ones. So we have here the database of extrasolar planets. They should go and look for this planet. They should compare, and they should think, why are there differences? How they could do a better job. And here they still have something to explore, which is a simulator of light curves, so that they can play around a little bit and compare with what they have done. So this is a really nice simulator so that they can change the parameters and see how it affects. And of course, we always want them to reflect on their work and communicate. So they should, at the end, make some wrap up of their activity and finalize with either a report or a presentation to the rest of the class. And this is our demonstrator for the discovery of an exoplanet. Do we have questions?
Yeah, I would like to ask if the light curves can give any information about the distance from the star.
From the planet to the star?
Yeah. From
like this? No, no.
Okay, thank you.
You're welcome.
From a higher point of view, if you know the star and you therefore know from its color and its temperature what its diameter is, so you can work out, if you know the diameter of the planet from the ratio, you can work out its speed, its radial velocity.
Yes, yes.
With radial velocity, you could work out a period, and therefore t squared r cubed Kepler's law gives you a distance.
I know you can go to the velocity. If you know the, well, you should be able to get the period.
And if you have a period,
have the period and you have the velocity.
But to know the velocity,
the star, if you know its color approximately, you know the mass of the star as well.
Yes, yes.
That's what the same information that gives you diameter should give you its mass. And if you get the velocity of the star, you can use that to calculate a distance. That would fit in. That sort of stuff would fit in with A level here. But not it wouldn't be one individual question. It would be something a teacher would guide students through.
No, yes, it would be going step by step, giving guidelines so that they could go further. Yes, that's something that could be added here, definitely. More questions?
No, thank you.
No? Then I think I'm going to give the word to Rosa. Are you there, Rosa?
Yes, I am. Thank you, Luisa. And thank you also for explaining a lot of things that I will be using in my presentation. So I can skip that and try to be a little bit more quick. Luisa, how much time do I have?
Wasn't it 20 minutes?
20 minutes.
Half an hour.
Whew, okay, I'll try my best. So, okay, now you control the participants and the chat, etc., right? Let me share my screen, but in order to be able to show you everything I want, I will share with you my full screen. I hope you can see my full screen by now. And I will start with a PowerPoint presentation. Do you see a slide thing? Okay. So I'll try to be very quick here. The idea here is to show you how you can introduce black holes to students, even if they are in the very beginning of their student career. So this exercise, as Lisa said, can be done going all through the all steps and even calculating math and everything, or it can be done for primary school kids, just for them to understand how we can discover something. And I've been doing that with kids from 3rd, 3rd and 4th grade, but more with 7th graders. And it works well just for them to understand, okay, I could be handling astronomical images myself. So the idea here is to go from, this is what we think a black hole is, which is a very nice image and everybody loves to see something like that, like we see in Interstellar and everything. But reality is far from this. This is what, in fact, what we see. If we're talking about a stellar mass black hole candidate, which is this little star here. Can you see my pointer, my mouse?
Yes.
Okay, so this is a black hole candidate, a very good one. But I mean, if you are looking at it, you don't know. And this is a very good question that you could already be asking me. How do we know that we are looking at a potential stellar mass black hole candidate? In fact, this is not a black hole candidate. This is the star that is orbiting the black hole candidate. So, which makes things a little bit more difficult. In this one, you see a few stars. I'm not going to show the movie now, but you have a few stars that are orbiting the center of our galaxy, which are showing very strong evidence that we might have a million or billions solar masses black hole in the center of our galaxies, and that can be used also for many other galaxies. So this exercise that you will be shown is talking about stellar mass black hole. And this comes towards the end of the life cycles of massive stars, which I'm not going to talk to you about, but I mean, there's plenty of information out there, or you can come back to us to ask more information about this. This is something that is very neat to get students started on black hole, to discuss, the origin of chemical elements, the star formation and the origin of chemical elements through the life of a star, and how do scientists believe that massive objects like neutron stars and black holes can form after the life cycle of stars. So you can try and explore a little bit how this is happening. So I told you that that picture is showing the point where we find a very good candidate, and what you see is this blue part, which is the star, but orbiting it we have this, of course this is an artist's view of a black hole candidate, and what is going on here is that there is a compact object here in the center, there is an accretion disk that is forming due to the strong gravitational field of this object. And this accretion disk is emitting a lot of X-rays. And this is how we detect these objects. One of the ways, I think, the most important ones to detect such silent objects. And what you see here is the mass of the companion star being transferred to the accretion disk. So these are things that we can observe in the various bandwidths. So if the object is a pulsar, then we will see accompanying the optical images, we also see radio pulsars. So they are pulsing in a very quick way, and we know that those candidates are probably, are for sure neutron stars, which we will observe several of them. The problem is that they are not, when they are not pulsars, and in that particular case, it's very difficult to tell one from the other, which one is a neutron star and which one is a black hole candidate. So we try to figure out what is the minimum mass that will allow you to say, okay, this is probably a very good candidate to be a black hole. And the reason why I keep saying candidate is because you want to see the final evidence, which is mass that disappear through the event horizon of a black hole, which is something that is virtually impossible to observe. So we have to have indirect evidence. As I told you in my presentation in the beginning of the week, the gravitational waves are helping us with the discovery and comprovation of such existing objects, or they will, at least in the future, when they are capable of measuring and finding the smaller ones, which are the candidates that we have. So how does it work? Well, what happens is that you have, so you can imagine that the star, I'll just go back a little bit, the star here is not a sphere, the star is distorted. So that means that if there is a difference when I see the star, okay, if I have a ball and I see it, if I rotate it, the brightness is going to be always the same. But if I have a pear-shaped lamp, then if it is this side, I will see it certain format or certain luminosity. If it is like this, I will see it differently. If it is like this, I will see it different. So you can tell while it's rotating that there is a difference in brightness. Also, the disk also emits light. So what happens is that in this diagram you can see, here you see that the star, which is now a pear shape, is turned to us and the disk is behind the star. So in this perfect scenario, the star is covering the disk. Then the system turns a little bit and now you see the star in a pear shape and you see the disk, and both of them are emitting light to us. So we have maximum brightness here. Then we have the disk covering partially or totally the light of the star, and you have a dip. And then you have again the both systems side by side. And then you have the star covering the disk. Again, you have a dip. So this is how we know that something is going on, that you have this ellipsoidal variation that is caused by this combined shape of the disk and of the pear-shaped star. And by using, the period and the orbital velocity that is obtained from other parameters, we will be able to calculate the minimum mass of this object. Okay, so we will go there. This is what the demonstrator is all about. Just to let you know, this is one of the most famous black hole candidates. The star, the companion star, is in the nose of the little drawing here. And it's the same case. You have a star, sorry for the Portuguese, there is a star here and there is an accretion disk and the mass is falling in the direction of the star. So this is what is going on. So I'm going to go back to the demonstrator. I guess you can see the demonstrator here. Is that true? You can see it? Okay, good. So here you see the introduction, and of course the demonstrator will go through. It's not a full introduction on black holes. You can find those very well done in many videos that you find in YouTube, and we can provide more information on that. But of course, everyone remembers that in 2017, there was the first observation of the shadow of a black hole on a accretion disk that was going right in the direction of what the theory was predicting for such a black hole. It's in a gigantic galaxy, M87. We already for several years, this galaxy is being studied for the suspicions of having a massive black hole. And you can see on the right, the simulation, and on the left, the reality. So this is really very good. So in this case, you are just sparking the curiosity of the students about this topic. And you also can talk about the ones that we know, the masses that they have, and the ones that LIGO is now detecting, as you saw in the presentations in the beginning of the week. And so there are several, in here also you have a link for an introduction to black holes, where you will find lots of information. And again, I'm available to support you if you want to implement this exercise with your students. I will walk alongside with you to support you. We have several cases of students that follow the path and even are helping now. We have Swiss students helping astrophysicists discover more black hole candidates. Okay, the second phase, what will happen is that you start talking about what I was describing to you, the binary systems and how they operate. And the students will be introduced to the fact that they will be exploring a real black hole candidate. So the data that helped astrophysicists define better the light curve of this black hole candidate is linked here in this exercise. And you will be able to, the students will be able to use them to reproduce the light curve of this black hole candidate. So the model is the model of an eclipsing binary. And in here, the students are requested to look at this curve and think about what's going on. So they see what I described it to you, two stars. This, in this particular case, is not a black hole candidate. It's just a binary system, two stars that are orbiting each other. And you will see that you know, there is a variation. It's not an ellipsoidal variation as in the case of the black hole candidate, but they can already start thinking about what's going on there. It's for them to discuss and to try and come out with their own hypothesis on what is going on in this particular case. Then you see the part of the investigation where they will have access to all the images. And what will happen here, so thanks Luisa for explaining this very nicely. They will also do photometry, but in this particular case, they will be studying 62 images of a black hole candidate. And what you see here is that star number 1, 2, and 3, all the images are the same, but stars number 1, 2, and 3 are the comparison stars. So we're going to take an average of these 3 stars, and then you have the star number 4, that is the one that we are studying. So they are going to measure the brightness of each of these stars and put in an Excel that is provided. It's linked here. I will show you the Excel in a moment. So they're going again to use the Salsa J software, and they're going to measure the brightness of these stars. Oh, for some reason, the nice pictures of Salsa J are not appearing here. We have to fix that. But you have, so you don't have to be an expert on Salsa J in order to do this activity. Salsa J, as Luisa said, is a very user-friendly software, and you just, you know, launch it, and you go there and you follow the steps that are here, and you can perform the measurement of the brightness of the stars, of each of the 4 stars that are here, 1, 2, 3, and 4. And you are going to put this in an Excel spreadsheet that has the space for you to put the measurements here. And what will happen is that in the end, you will have a graph automatically appearing that will it will show you what's going on with the different stars. I will show you that in a moment. So you introduce Salsa J. You can find Salsa J here in this link. And as Luisa said, there will be some further support for you to learn how to use Salsa J, which is a very powerful software, not only for studying black holes and everything, but also to introducing you to other very nice things related to astronomy. But in this particular case, here are the steps. Even if you never touch the Salsa J, you will be able to follow the instructions. And before I have to give the floor back to Luisa, I will do one measurement with you so you understand how this is done. So this is the result. And although scientifically there's many things that can be changed, even a primary school kid can, click on the image, measure the value, and put the value in the Excel, and this will appear automatically. So you can see that there's something going on here. Something is happening. You see here the average of the 3 stars that are the comparison stars, that they don't really vary. The variation that you might see have to do with our atmosphere and not with the star per se. And here you can see the variation of the star number 4, which is, mimicking the ellipsoidal variation that we expect. So the next step will be for them to use, of course, you don't have to do that if your students are not there yet, if they're not studying Kepler laws, or if you don't have these equations, you don't have to go there. You can stop the exercise here, and you can help, you can discuss with them what did they achieve? What do they think about that? To me, this is very powerful because it means that I can point my camera to a random star in the sky, take several pictures, and analyze the brightness across, a long period of time. And if I have such a candidate, which in this particular case have a period of 4 hours, I can see the full orbit of the binary system, and I can depict this graph. So you don't have to be a super scientist to be able to discover a black hole candidate. The same goes for exoplanets. Okay, so this is something that is empowering for students to understand that when they say, oh, science is not for me. Yes, it is. It's just a matter that you understand the things and you learn a little bit of math. But of course, if you are working with secondary school students and you have the possibility, you should go a little bit further. You should analyze, have them analyze the curve and discuss with the colleagues and try to compare with the hypotheses that they have done, the discussions that they have found. And they can, roughly estimate the orbital period of the star and use this formula to calculate the limiting mass, the minimum mass that this black hole candidate can have. Of course, you have to give them this value because they are not doing spectroscopy here. They are not studying the velocity of the object. Actually, in fact, in science, some people are going to do the optical, some people are doing the calculation of the orbital velocity. Sometimes you can do both of them, but people combine their measurements, their values to reach out a conclusion. And they can then find out the mass of the black hole candidate in solar masses. And then they can conclude, and here is the full calculation. So you as a teacher beforehand, you can have access to that and you can follow up the calculation, and they should reach out a value approximately 6.1 solar masses, which is very close to the value that the scientists have for this object. This is actually a very good case because the collection, usually life is harder than this because you don't collect all the images in the same night. You have to combine the images. You have to do what we call phase the images. And life is not as easy. But in this particular case, because the orbit is only 4 hours, the 62 images that you have in your possession are covering more or less the full orbit of the two objects. So it's really a very good case to introduce your student without having them sweat to do a little bit more complicated things. It's not very complicated, it's doable, but it requires a little bit more understanding of what it is and a little bit more work. But I mean, you can do it, and if you decide to do this as an astronomy project with your student all year, we can work together to materialize that and have this taking place. And in the end, you have a few more links here where you can explore more. For instance, you can explore the Worldwide Telescope and see which one is the star that is, you know, where this object is orbiting, where in which constellation, the direction of which constellation, which other objects are there. You can also have your students read at least the abstract of the papers where this object is being explored by scientists, so on and so forth. You can also find more black hole candidates. And if your students are really interested, and if you want to do a near long, you can again talk to me. We work with the team of the Folks Telescope, and they can provide some telescope time for students to help scientists to observe such candidates. This is already happened in the past. Before I finish, I would like to go to Salsa J. So I guess, can you see Salsa J in my screen? Yes? Okay, so I will just open one of the images. Let's see if this is a good one. Okay, so this is one of the images that you are going to have access to. So I just launched Salsa J. And as Maria Luisa said, it might be a little bit tricky to have Salsa J working just because it's an old software, and people have been building patches to help when the operational system changes and they change the place where they store all the information. Sometimes it's hard to find, but there are easy ways to solve this and help you have Salsa J working. And when that happens, you can then, you know, I'm going to zoom in the image. You can see the 4 images that I showed you and that are in the demonstrators. They are here. No way to miss, it's clearly here. This is star number 1. This is star number 2. This is star number 3, and this is star number 4. And I'm going to click in photometry. This is the photometry shortcut. If I click in this plus button, I can come here and force the radius of the star to be 4, as Maria Luisa suggested. Also, there is a full tutorial explaining how you know the number is 4 and not 5 or 6 or 10. There are ways to discover that. And I click here in the photometry. I'm going to select this, and I'm going to clear, so there is no measurement there. And if I click in the 1, 2, 3, and I go to the star, I click in star 1, star 2, star 3, and star 4. Actually, this radius is still very big. So, it didn't, okay, I forgot to say force radius, and the number is 4. Okay, so I'm going to clear those values again, so there is no confusion. Those are wrong. And I'm going to click here again in the 1, 2, 3. And now you see it's much better. I don't know if you can see the little curve around the star. So I'm avoiding a lot of noise from the sky. This is number 4. And here I have the intensity of the star that I can then copy and put in the Excel spreadsheet that I showed you before. So this is a pretty clean way of doing this exercise and measuring the brightness. And once they have all the measurements, they can then see the light curve. And I think I'm going to stop sharing to see if there is any question. If I was too quick, Luisa, please take over if you think I forgot anything that you have included in the demonstrator.
You have one question?
Okay. Students usually make is if a black hole connects with another dimension. Oh, Okay, that's a very good question. Actually, my master's degree was about studying the interior of a black hole candidate, and it's a very interesting study to tell you. The fact, the reality is that, well, now with the many evidences, we are beginning to become very convinced that black holes exist. But up to now, we are not even sure that they really exist. We know there's something there that provokes all these weird phenomena. But we have never spotted a black hole event horizon. We don't have evidence of that. So to be very honest, we cannot say 100% sure that black holes do exist. They do mimic a lot of things that are going on that the theory is predicting, but we cannot be 100% sure. Now you ask me, they ask if it can connect to another dimension. Well, what if I told you that we could be inside of a black hole or a white hole? To better say it, which is the opposite of a black hole. It's a place where light can go out but cannot come back. What if the universe would mimic that? And that was my master degree, was repeating the calculations, and the interior of a black hole is very similar to our universe. It's weirdly similar to our universe. And so you ask me, okay, what happens inside? Can we go to another universe? We don't know. There are theories, you use Einstein's equation, you can think that maybe there is a way to go from a black hole to a white hole, but we don't know. This is just a theory and sometimes a speculation. We don't know that yet. There needs more science needs to be done, and to be honest, more funding. People need to understand that studying these fundamental things, it's important even if they don't translate into immediate profits. But when I was preparing the presentation for this beginning of this week, I was shocked to see that the evolution in outreach and education material on black hole has stopped many years ago. It's just very little thing coming out. That means that people are not investing in black hole research. So that's a pity, because we know nothing. We know nothing, and we should. Some scientists even say that particles, some elementary particles, like an electron, for instance, could be a black hole. So this is interesting path to go. Could be nothing, or could be something worth exploring. So another question. We do subtract. So the program is doing this automatically. When Luisa mentioned this to you, what Salsa J is doing. Okay, let me share my screen again for a moment. Desktop 2. Okay, share. When you see these parameters here, I'm telling the program is calculating automatically the sky radius, the sky value, and the radius that the star should have in this picture. Okay, so the system is calculating this automatically. You can then, of course, try and work out and clean it a little bit, but Salsa J does this calculation automatically. And the objective is exactly to allow students in a painless way to reproduce the scientific measurements. So that is indeed taking into account.
May I say something here?
Yes, Manolis.
This is actually a very nice way to introduce signal and noise in general for students. Meaning, for example, such a technique applies not only to astronomy, but to seismology, to every physics topic where we have signal and noise. So you trigger on the noise, okay, and then you remove from the signal plus noise area. Am I correct? Isn't this what Salsa J does here?
Yes, that's what Salsa J is doing.
Mm-hmm.
Yeah, that's also, but of course, life is more complicated than what you can do with Salsa J, but Salsa J is doing that automatically, yes. Is it, okay, there was another question. No, okay, that's it. One question remains, the black hole connects another dimension. For some reason, I lost.
Rosa, it was about the software. I replied, I hope I did well.
Okay, thank you. Okay. So yeah, the technique for exoplanets and black hole candidates is the same, and it's the same also for other objects in the sky. And we are currently working with a team from Canary Island and the National Schools Observatory to produce an exercise, a different one, where you have a black hole, you have a cataclysmic variable, you have a supernova, and you have an exoplanet. And the students who have divided in group, who have the images, they will make the light curve and they'll have to discuss which one belongs to which. So this is something that is coming, and we will knock your door to say, hey, teachers, please use that with your students. Okay, Luisa, back to you. The floor is yours.
Well, actually, I'm going to give the floor to Giulia, right?
Yes. So I will present. Wait, I need to share the screen
Wait,
myself. Oh, can you allow me, please? So in the meanwhile, I'll
now you can. Now you can.
Ah, okay, thanks. Now I need to find it. Just a second. This is it.
We have a question asking, is there any relationship between black holes and dark matter?
No, sorry, you've seen the wrong thing. How do I share this one? Can somebody reply to the question so I get the time to figure out what to do here?
From what I know, a black hole is an evolution of a star which obeys a specific mass criterion. But dark matter is something different.
Yeah, Manoj, in fact, some scientists think that the small black hole, the micro, it's called the machos, could be part of the dark matter. They could be there, but we don't have any evidence of that. And it's not likely, but it could be part of it, a very small part of it, if we understand what they are and if they really are what we think they are, because yeah, that's a very complicated area to be studied right now, because there's astroparticle physics is bringing a lot of new information and also trying to put some light on dark matter, and we are changing the way we understand that. But yeah, maybe this is something that you will explore in the other sessions.
So do you actually see the demonstrator?
Yes.
Just the demonstrator, I hope.
Just the demonstrator.
100 windows.
Yeah,
open.
just the demonstrator.
Okay. So this demonstrator I'm presenting is about calculating the age of the universe and the Hubble constant. So we will go through Hubble's experience and measurements. Just a brief forward. So you will notice in this section about astrophysics and cosmology, I believe, I hope, a consistency, especially methodology. So this demonstrator as well will try to mimic somehow to give a flavor to the students of like the daily work of an observational astronomer. And the idea is that not only is more engaging to take data and analyze them yourself, but this could, let's say, some of the students may be interested in the content, but some other may be more engaged by the methodology itself. So we will analyze real data from real images of the sky. It's a bit less interactive than Salsa J, because this was taken or inspired or taken from an exercise developed at the Gettysburg College in the United States, but we simplified it by having videos and images extracted that the students will analyze. It will also introduce a lot of basics of cosmology and of astronomical methodology. To name a few, the basic concepts that students will get familiar with are the magnitude, luminosity distance, standard candles, which are fundamental in astronomy, Doppler effect, redshift, and obviously, so the what is the expansion of the universe, what's the age of the universe. And also one point that I find interesting is that in this, as in many other astronomical discoveries and experiences, there is a smart way to combine and techniques. So we will use, again, absorption lines, which are connected to chemistry. So you can kind of approach these also from that side. If the students are doing some chemistry and know about the spectra of any object, in this case stars, and about the chemical composition. One last thing is that, so Hubble basically discovered that there are extragalactic objects, that we live in one of many galaxies that look similar to us, like the Andromeda galaxy. And he discovered that the universe is expanding, is not static. So this is, I think, one of the main discoveries that we ever made. However, he personally was not awarded the Nobel Prize just because at the time, the Nobel Prize Committee did not include astronomy in the disciplines worth a Nobel Prize. However, I think it's worth mentioning that in 2011, 3 physicists, so Perlmutter, Schmidt, and Rice, did get a Nobel Prize because they demonstrated that the expansion of the universe is actually accelerating. And they did it by using standard candles, in this case, supernovae of type 1a. So in some sense, it's something that goes in the line of Hubble's discovery. With no further ado, let's get into the demonstrator. So you're now familiar with the structure of each demonstrator. So this one starts with a brief history of Edwin Hubble's discovery, so his observations and how he could infer that that some of the objects that were called nebulae up to that time are actually other galaxies outside our own galaxy. Its text, as you can see, is a very brief, simple history. And then there is an introduction to the idea of using light spectra to understand some of the basics of these new objects that Hubble discovered. So what Hubble did, he combined his observations with spectral observations. So taking some of the absorption lines of stellar spectra, it was seen that they have the same spectral shape, but they are shifted in wavelength, and they are shifted towards the red of the spectrum. And basically this means, as you surely know, that these objects are getting away from us. So these galaxies that Hubble discovered are receding from us, which means, in turn means, that the universe is actually expanding. So this is all that it's in this first introduction about the expanding universe. You have here a very simple representation of the Hubble diagram. So basically you have distance versus recession velocity of the galaxy. And what Hubble found is that everything falls in a nice straight line. And basically the slope of this straight line is what we call the Hubble parameter H0, or the Hubble constant, even though nowadays we're not so sure it's a constant, but let's call it the Hubble constant. And we will see that just by using the Hubble constant, so basically the students, at the end, I'm getting a bit ahead, so in the end, the students will exactly reproduce this diagram. They will calculate the slope. This is just the slope of a straight line. It's quite simple. And basically just by inverting it, so 1 over H0 will give you a pretty good estimation of the age of the universe, and we will see why. Then, just for you a bit more technical, you will see this gray area. These are guidelines for the teachers. So I just wanted to show, maybe this was shown before, but that there are two ways to visualize a demonstrator. This is the teacher view, and you can, I just want to show you that there is a student view. Just a sec. And in the student view, of course, you do not have the gray areas, and you will see there are some other differences. So here we tell the students what we want to do. So we want to calculate the Hubble constant, and we want to calculate the age of the universe. And there are some questions to start the conversation and to engage them in thinking about the meaning of Hubble's discovery. So let's go next. So this is what I wanted to show. We introduced in some of the demonstrations, you will find questions that the students have to answer while they progress. And this is the student's view. And if we switch back, you will see that for the teachers, you will see what the student gets when they, whoops, next page. Okay, so there are already the answers. So when the students choose, there are already built-in answers to the questions. Okay, so in this phase, but I already told you, we highlight the goals of the activity. So we want to estimate H0, and we want to calculate the age of the universe from it. Again, some questions to engage discussion in the classroom. By the way, you can choose whether students do this exercise on their own or they form small groups. That's also possible. Now, here is a brief explanation of what we will do. So what we will do, and you will see it in the next session, we will actually take data from real images of the sky in the optical. We will create the spectra of a few galaxies, and we will see the absorption lines, and we will calculate the redshift of these lines. And from that, we will basically replot the Hubble diagram. Again, here there are some further explanation. For example, we put some focuses on some concept that might be not so familiar for the students. For instance, what a parsec is, and you can decide according to the level of your class and the interest of your students, the level you want to go into. You can further expand or keep it very simple. Here we explain again that we will use absorption lines, and we give the basics of the two absorption lines that we will use, which are the calcium H and K lines. Okay, so this planning and investigation is the data taking part. The way we structure this is through videos and then ready to use images. Now, this is a bit long if I have to explain everything, so I will really just give you an overview. Basically, what the students will do, I'll scroll down, you will see, I'll come back to this part. They will have, just a second, 1, 2, 3, 4, 5 different sources to study. These are 5 different galaxies in 5 different fields of view of an optical telescope. And the way it works is that the first source we will study together. So the students are guided through the whole process of knowing what we're doing, data taking for the first source. For the remaining 4, they are given the working images and they will work on their own. I will not show you the entire video, but what the what the tool that we will use is a very good simulation of the operation of an actual telescope. So I will just start with the first one. I think you can see and hear. Do you see this? If it works.
We see, but we can't hear, because when you share, we hear.
The dome opening. So this is the actual dome opening, and then basically you see the procedure. Everything is explained in the text. Everything you're seeing now is spelled out in the text of the demonstrator, so they can read it first, and then you look at this. So you see here the coordinates of the field of view that was chosen, and then you basically see what instrument is used, and so on and so forth. I will not show you all the videos, obviously, but I just wanted to give you a taste. So you start the tracking so that the object doesn't move from your field of view. Otherwise, as you know, the sky moves, and the source will go out of your field of your instruments. Yeah. Aperture. Wait. How do I exit from this one? Why is it? Oh, okay. So as I was saying, everything is thoroughly described here, and you go on with the videos through the data taking. Basically, you choose your source, you activate then the spectrometer, and the spectrometer takes data, and you will see something that was mentioned before. You will see the number of photons that enter the telescope, and you will see how you need a certain level of light to be recorded by the telescope, and a certain time to elapse in order to have a good signal to noise ratio. So this is explained in some detail. As you can see, I'm trying to be quick because it's a bit long, but you see here, everything is explained. Everything that they see in the videos is spelled out. So without seeing the video, but basically what you get in the end, now this is almost all noise, but what you see is this. So you have the photon count, you have the signal to noise ratio, which is too small here, the integration time, and so on and so forth. And this, you will see that this spectrum gets more and more clear as the integration time goes by, because the signal to noise ratio gets better. And then what they will work with is images like this one. So you see that the lines are starting to be more evident. You have all the data you need. You have here photon number, apparent magnitude, which is something that we need to use, and well, the galaxy name just to identify them. So now, again, this is what the students will see once, and then they will work with the final images. Basically, we save the spectral images and we zoom in, and with the cursor, we identified already for them the lines. And what you see is the wavelength of the center. It's not so easy to identify the center of the line, but this is the wavelength of the center of the absorption line, the H and K absorption lines. And they have the wavelength here. So now they perform the investigation. So now they have seen how we get there one time, and then they are given 4 more fields of view with right ascension and declination. By the way, right ascension and declination, also basic concept, they are introduced, even though not in great detail because it's not necessary, but this is also another concept that the students will learn. So they are given the coordinates of the part of the sky they're looking at, and they are given the plots they need. And what they need to do, and now it's a bit basic, I realize, but they will have by themselves to look at the, let's say the dip here, the peak of the absorption lines, and extract the wavelength. It doesn't need to be super precise. So we go, this is source 3, source 4, you understood by now, and source 5. What we did, I will say actually if it's better to just download the spreadsheet as Maria Luisa was saying, but we put in a built-in spreadsheet that they can fill in as they go on in the analysis, or in the data taking, we'll do the analysis later. So they have the galaxy name. Now, we made some assumptions. In particular, to perform the calculation, you need to know the absolute magnitude, so the intrinsic luminosity of the source. And we set it as an hypothesis, all the same, all to -22. You don't have to worry about this. Then they will put in everything that was, or that they can extract from the plots, the photon numbers, the apparent magnitude. We will see then how they will calculate the distance in parsecs, megaparsecs, and the measured wavelengths. And then they will calculate, this will come in the next page, the shift in the wavelength from the lab measurement to what they measured in the exercise, and extract the velocity of connected to the two lines and do the mean of this. So what they need to do is start to fill in this spreadsheet, and then, as it's written here, remember to download it locally, because once they move on to the next session, they will not be able to come back. So they need to download the spreadsheet with all their information. And now we leave the data taking part and we go to the analysis part. So this is exactly what an astronomer does. They prepare their sources, they go to the telescope, they have a limited allocated time, they hope for clear nights of observation, they observe their sources, they don't write down, everything is automatic now, but they basically write down all the data that they can take, they go back to their office and they analyze the data. And so the analysis part, of course, uses some maths, but as you can see, this is very, very basic maths. Nothing special here. Don't be worried by the log. Actually, you don't even need to know what a log is so much, because this is really like a linear equation, and then you only have to do 10 to the whatever number you get here to get the luminosity distance. You can call this x or whatever you like. So what are the parameters we need? As I said, from the absolute magnitude that is given to the student and from the apparent magnitude that they get from the data, they will be able to calculate, as Hubble did, the luminosity distance of the source. So they will get an estimation of the distance of the source. Then they will need, and they need to mark it down both in parsecs and megaparsecs, which is 10 to the 6, is super difficult. And they need to calculate the recession velocity of the source. Now, we do this assuming that the redshift is due to a Doppler effect. I went quickly, but in the first introductory part, everything is spelled out. So what they do is they use this simple, very simple equation where c is the speed of light, and they have the value right here. And they do, for each line, for each source, they do the measure wavelength minus the lab measure wavelength. They get the delta lambda. This should be a lambda, but it wasn't allowed to use Greek letters, so delta L. And then they divide by the known value, and they extract the velocity for the H line and the K line. And then they simply do like an average. They extract the mean velocity is 1, the other divided by 2, and that's it. And they write it down. So now we have some questions here to make sure that they understood what they're doing. And now we're ready to plot the Hubble diagram. Once again, there is a already built-in spreadsheet for this. So what they need to do for each source, they just write down the distance they calculated from their data and the mean velocity they calculated for each source. And then here, they will have the Hubble diagram. So as a function of the distance from us, the velocity of the source is plotted, and if everything went well, they will see all the points kind of fitting a nice straight line. They need, this is something they need to know, they need to fit a line through their data points, and from that, they will simply extract or have the slope of the line, which is h0, okay? Basically, well, we also spelled out, it depends how you want to do it. Some fits will automatically give it to you, but otherwise you just you plot the line and you take some values on the line of D and V, not the data points, and you just use this simple relation. So h0 is just V divided by D on the line. Now we go to the even more interesting part, which is that in like one simple step, from this, you can actually evaluate the age of the universe. So in general, right, T equals D divided velocity. So really immediately you get that an estimation of the age of the universe is simply 1 over h0. And that's all they have to do. And you will see that it's quite amazing how powerful this simple tool is. There is a tricky part, which is conversion, because the Hubble constant is measured in kilometers over megaparsecs over seconds. We would like to have the time at least in years rather than seconds, because it's a lot of seconds. And so to facilitate the thing, they could have looked it up, but okay, we made it easier. So here is the conversion parameters they need to go from megaparsecs to kilometers, and then from seconds to years. We're basically done. Then there is the reporting part. I'm being a bit long. Okay, so they're asked to write a simple report, and possibly this would be interesting if they want to record either a video or an audio with their conclusions. This might help in particular those students that might have some problems with talking in front of the whole class. It might help them to pre-record, let's say, their speech, their presentation, and it's a bit less embarrassing for the shyest of students. And then there are some final questions for them to discuss with their classmates on what they've learned of the different explanations, and also on whether or not this was stimulating for them. So do you feel you have gained relevant information of the physics of the universe? Do you feel that you have gained relevant insight on the daily work of astronomers? I want to highlight again that yes, of course, we would love for them to be able to go out after this and be able to explain the Hubble measurements, the age, like the expansion of the universe, everything that they learned in terms of content. But even more, we would love for them to get like a spark of interest for science, for the scientific method, to just be more curious than they were at the beginning. That's already a lot for us. And then one last part is, and this is, there is a whole world of cosmology in this one simple question. They could, if you feel like it's appropriate, they could do some literature research, and they will find out that there are different values of H0 nowadays, depending on the different methods that you use to calculate it. We have seen just one, but actually there is a strong tension nowadays in the different values of H0 that you obtain with different methods. And this is cutting edge science. We are actually now hoping to maybe solve this problem with gravitational waves. We are here really at the forefront of cosmology, and this could be an interesting topic to discuss. And again, here are some suggestions for the teachers if you want to further the discussion with your students. And that's it. Sorry, I was a bit long.
Fantastic, Giulia, thank you.
Hopefully it was clear. I don't know if there are questions.
Yes, you have a first one.
Wow. Not being an observational astronomer, does anybody know if we can use a homemade spectrometer? I guess it depends on,
You can get a homemade spectroscope to make to see the spectra of a lamp of light in your street, but or the over lines of the sun.
The sun is
but of a distant start, you need equipment. Homemade spectrometer. You're going to waste a lot of money and do something that is far more expensive than if you buy an equipment with that purpose. But even so, it's not a common practice.
Yes, also the point is, Wilson, if the resolution of your spectrometer is good, actually, because, for example, so if you have high uncertainty in locating the peak you are searching for, then you might not be able to observe effects for small distances. So, perhaps. May I ask a question as well?
yes, don't be nice.
I'm always nice. So, actually, this is very nice, and it might be able to be connected somehow to the curriculum of classical mechanics for 15-year-old students. I'm asking this actually because I'm not sure. I just thought about it, and maybe we could you could offer me some insights, everyone. So I was thinking that when we have an object in which we apply a constant force, its velocity will change with linearly with time. So if you do the math, you will see that its velocity will change with the square root of distance. Am I correct?
Who are you asking?
Okay, accelerated motion. So when we give this equation to the students, saying that actually the velocity changes with linearly with the first power of distance, then what we could ask them would be, do you think that there is someone out there pushing objects away from us with a constant force, for example? And
it's very interesting. It gets a bit complicated very fast, but it's interesting.
You think so? Because if you take it, for example, the balloon example, or if you take a membrane, you take a membrane and let's say that you mark with your pen or something 10 equidistant points, okay, with let's say 5 millimeters distance the one from the other, and then you start stretching the membrane. You will see that if you stretch for let's say 5 seconds, you will see that the closest ones will stretch less. For example, let's say that we double the distance, okay? So the first with the second will now be apart twice as much, so 1 centimeter, but the first with the last, the distance will be doubled as well. So if it was, let's say, 5 centimeters, it will become 10. So it will appear to us that they are getting away from each other more rapidly. So maybe this could give, thank you, Adina. Maybe this could give people and a sense of how we could depict it by an analogy, at least. Maybe, I don't know. We also have a question from CD.
Yeah, I was reading that, which maybe goes in the same direction somehow. So first of all, I'm not sure that this is the answer you're looking for, but just to be clear, that Hubble did see that the farther you look, the fastest galaxies recede from us. That's exactly the Hubble diagram, meaning that you see that with increasing distance, velocity is also increasing. This is now not exactly this, maybe the same thing you're talking about. Maybe I'm not sure I'm getting this right. So I'll give you two answers. So so in the range where we are using Hubble's technique, let's say, everything holds. And with these sources that we chose, it will hopefully, with some errors of course, but they will hopefully all, if the students take the data well, they will fall in line in the Hubble diagram. Then of course reality nowadays, we know, it's way more complex, and that's what I was saying, that there is it's a whole field of cosmology to understand the Hubble constant, whether it's a constant or not, because there is a tension between different measurements. And one of the things is, when we measure it with the CMB, we're looking very, very, very far away when the universe was a baby. And when we look at galaxies, we are somehow looking at not really nowadays, but much later in the life of the universe. So is the tension connected to this? Is the tension connected to something else? This is something that I think it's very interesting that you might discuss if students follow. You might discuss at the very end. However, it doesn't impact the exercise per se. Was this the answer you were looking for?
Well, the exercise about the age of the universe is what we expect. We do that in the courses over here, but it's for me personally, because the Hubble constant isn't actually a constant.
Yeah. Yes.
So surely that would change the age of the universe. By that calculation. So the calculation is made on assumptions, and it gives us the answer we like. But is that by convenience, or is that just a fluke, or is there something more to it than that? Because surely, if the Hubble constant, if dark matter was more considerable, then expansion slows down, the Hubble constant decreases, and the age gets larger. But if dark energy takes over, Hubble increases, and therefore the universe gets younger by that calculation. Is that correct?
Go, Manoli, sorry, I interrupted you.
Yes, one thing is that the Hubble's constant is changing over time, because the radius of the universe is increasing at a constant rate. Okay, but it doesn't change with respect to space. Okay, so it is a constant in space, but not in time.
Got me. Okay. Right.
Okay.
No, but I think he was talking about time. That's the point.
But here we measure with respect to space, with respect to, so I think that here it's a good assumption to use H0 as constant. I don't know if this helps. Also,
in fact, sorry, Manolo, this debate is going on since the 50s. Actually, there is a very good book called The Big Debate, where the Hubble constant was being discussed. And actually, a couple of weeks ago, a new article came out with new measurements that extend further away, because there's more complicated things like if the supernovas are exactly as we think they are, if there are other types of supernova, if we can use other standard candles to measure this. So this is, but it in fact is a very good model that helps predict in local areas the results that we see. I mean, you see the graph that Hubble himself made. It's an amazing thing. And then, okay, you have more power. You see that it's diverging a little bit, but you know, this is how we go with the scientific technology evolves. You get better results, right, Giulia?
Yeah, and now I'm seeing probably the confusion, because I went through it a bit quickly. So I said that we would talk about standard candles, and then I kind of glided over it. So Hubble himself used this type of stars, which are called Cepheids. They are standard candles in the sense that we know the properties of the stars. They are quite reliable. So from the properties of the stars, we can then evaluate somehow the distance, because we know that they behave always in the same way. So we think we know their intrinsic luminosity and the way it changes and so on and so forth. This is what a standard candle more or less is an object that you think you know well enough and that is stable in its behavior. So when you put it in different places in the universe, and now I'm thinking not, as Manoli said, not in space, but in time. So farther and farther away from you, you can say, okay, but this is still the same object. So the differences I see are connected to the distance. Now, these standard candles, they only work in a certain range of distance, right? I think this is what Rosa was also referring to. And maybe I was too quick on this point. So basically, almost each method we have in astronomy to calculate distances changes with the distance range. And so within the range of applicability of the Hubble methodology, everything holds, right, Rosa? I think this is what you were referring to. Then when you go farther away, you need to find new and smarter ways to calculate distance and velocity. You cannot use that method because you're technically limited. You actually really cannot use it. It's like the parallax. I don't know how many of you are familiar with this. So with very, very close by objects, we started by using this distance measurement of the parallax. So basically the shift in position that you have by the fact that the Earth has an orbit. So, you know, like stereoscopic view, like you look at the same object from two different points, and from that you infer where the object is. But this is only suited for close by objects. And the farther you go, the smarter you have to be to find new probes and new ways to calculate the distance. So that's exactly the problem with the Hubble parameter. Let's call it Hubble parameter, that in different ranges of distance from us, you calculated, you estimated with very different methodology. So then you have to understand whether the difference you find, which is sometimes a big difference, there is a huge tension, is connected to whether you're not understanding what you're doing exactly, or rather to intrinsic properties, changing properties of the universe. Does that make sense, what I'm saying? And this is exactly the debate, the ongoing debate that we have today on the Hubble parameter. This is cutting edge. So I think this is extremely interesting. Again, I think it should be left for the discussion part, because this is ongoing research. We do not have one answer. It's like, does the black hole lead you to somewhere else? We don't know. We are studying it. And what we do know is that we have different measurements. They do not, there is I don't want to say they are in contrast, but there is a tension between these different measurements. And we are trying to see why that is. I mentioned that we have a new tool, maybe, which is gravitational waves. We have one more independent way of inferring the cosmological parameters. Hopefully, in the next few years, this tool will tell us where we stand in this tension about the Hubble parameter. I hope I made it clearer and not more confusing.
Yeah. May I ask something? I remember that when we see the plot of Hubble, he fitted a straight line. So he said, okay, this is the slope. So this is some standard laboratory physics.
No, don't ask me about the outliers.
Yes, it needn't be actually a straight line. I mean, he did some guesswork. He said, okay, this is it. I think it fits best. But, you know, with more data, he might say that it was a bit of a second degree polynomial, for example, or something. Or let's say something with a slowly decrease in slope or something. I don't know.
At this distance, look, guys, look at this. Oops.
No, but sorry for that, Giulia. No, with more data, it became very clear that it was, using this effect, it was a straight line. There was no question about that. The question was that this was a very short distance. So we could not make any prediction for things that were farther away, but in the closer area of the universe, it was a straight line. Actually, there are some graphs, some papers that show this results later on with the error bars and everything, which the fit is truly amazing.
I wanted to point out that we are not going very far here. Does that kind of answer your question?
It just means there's a lot more. It's knowing when to stop getting too involved. There's a difference between proper research, as you're doing, Giulia, and there's also the difference between what we have to do in high school.
No, that's why I would limit myself to this. It's a nice linear plot with very simple math, but it's worth mentioning that, first of all, probably that's the best way to do it. We are talking about scientific methods, so it's probably best. It's a bit introduced here, maybe not spelled out completely, that each methodology has a range of applicability, and we should say and know that we are doing this thing that works very well here. This is like Newton and Einstein. Sorry for going a bit sideways, but you know, like, was Newton wrong? Not at all. He was exactly right in the limits of the applicability of his theory, right? I mean, Einstein's equations are more general, but you can make assumptions, reasonable assumptions, to boil them down to Newton's equations. Is it clear what I'm trying to say? So everything has an applicability range. And then what happens when you go further out? First of all, you need to find new ways. And then the interesting part is to connect the things. And this part of connecting, we're still in the process of doing. We do not know everything, thank goodness, otherwise there wouldn't be any fun. And this is cutting edge research. And the students, I think it could be interesting to tell them, look, even with this very simple thing, you already get a taste of what people are studying right now in a much more refined, and, you know, like the actual data taking and analysis is not as simple as it's shown here, but you already get so very close to the edge of what we are studying today with 4 equations and like 4 data points or something like that. It's kind of amazing. Also, you will see, if you do the calculation, if everything well, if you do the calculation of the age of the universe, of course is like an estimate, but it's not that far off. It's it's quite close to what we know from other. Of course, there is a difference, but again, it depends on how much detail you're interested in. I mean, there is a difference between, I don't know, like you can say 13.9, 13.7, 14.1 billion years. It's there lies, the devil is in the details. I mean, there lies everything we are working on today in cosmology. On the other hand, for a student in high school, 14 billion years, it's good enough. 13 billion years, it doesn't make a difference between 500 years or I don't know, 25 billion years. Do you know what I mean? It depends on what you want to convey. I think 13 or 14 billion years are two perfectly reasonable numbers, both of them, to give a taste that it wasn't like 5,000 years ago, for instance. Does that make sense?
It's what it has to be.
Any more questions? So we are already here for a little bit more than 2 hours. I'm going just to talk like in 5 minutes about the 2 other demonstrators, not really going through them, but just to give an idea of what it is, especially because one of them is probably one of the simplest ones. And since we have teachers from primary schools who might have been more scared with the previous demonstrators, they might like to see something that maybe they can relate to more easily. Although our idea is that all these demonstrators should be we should be able to put it in all levels. So I'm not going to take much time. The ones I would like to show you are about the sun, but I'm going to show you the one that is easier. This is the one that is called, Does the Sun Rotate? And the idea is to talk a little bit about the sun, its relation to the Earth, and some characteristics. Why are we interested in studying the sun? Is the sun like a quiet object in the sky? And we are going to show some images that they understand that the sun is active, and it has some features that we can see with really nice images. So that can be done for any age. What we are going to explore is how scientists try to get information from data, and sometimes it's very tricky to be sure of what they think they are seeing. So you don't really need to know a lot about the sun, and the demonstrator is a nice excuse to talk a little bit about the sun as a star, as an active star, that things do happen there, and it's not just that yellow thing that we see every day. So I'm going to stop sharing this because I'd like to share. Share desktop. Sorry. I'm going to take this. So after introducing a little bit the sun and its activity, we are going to ask them to use, for instance, Salsa J. I'm not going to use Salsa J. I'm going to do something very, very easy, which is a preview of images of the sun that have something there. And even the young kids can see what happens when time goes by. So what will they say? The sun rotates, right? So obvious. We see things that are going round. Great. But then we give them a collection of images where they also see the sun rotating. Oh, what was that? So there's something over there that is passing, also maybe rotating with the sun, maybe not. And so what we want with this demonstrator is for them to realize that what they see at the first place, which is the sunspots, and they are sure that the sun rotates because they see it. Then they see another object, and maybe they say, no, that's something that is just passing in front of the sun, especially because it's so neat, it's a real circle. They can think that it might be a planet or something else, but it shows them that they have to argue why they think that the sunspots are in the sun and why the other object, they might think that it is not, doesn't belong to the sun, it's just passing through. And we're taking them to Galileo's thoughts. So it's a demonstrator where they put the shoes of a scientist that sees something, has a first theory, and then sees another thing and has to really understand what is happening. So our idea with the demonstrator is that they can, oh, I don't have it anymore here. I'm not sharing, sorry. Is that they have to get arguments to say why they think that the sunspots belong to the sun. And we suggest to do hands-on activities, for instance, putting a ball, a real ball, gluing something there and try to look at it from far away and then just put something passing so that they can explore how, from the point of view of someone that is observing far away, they can distinguish if something is just orbiting, like in that case it was Venus that is orbiting the sun, and the sunspots, that is how we, one of the ways that we calculate the solar rotation. So I just wanted to give this quick demonstrator because I think it's something that maybe the primary teachers might like to look at it and see how they can explore. We also have the other one, which I'm not going to go through it, which is to determine the rotation velocity of the sun, where we suggest a couple of ways to explore the observation of the sunspots in the sun. But so it's already been more than 2 hours and I'm sure everybody is getting tired. I think that we have already seen what the Astrophysics and Cosmology module has to offer. What we are going to do after this with the working groups is to try to get educational resources produced by the teachers that they can use in the classroom. We have right now 31 participants, so I'm sure we have here more participants than the ones of the working groups. And I'd like to thank you for being here for this session. But at this point, I think that our session can end and we can stay with the working groups. I'm going to put here what I have as our working group in this module. Let me just share. Can you see? So these are the teachers that are joining this working group. I didn't see all of you here, but there are some names that I can't recognize. So if you have a different name over there, I might have not spotted you there. We are going to have 4 groups, 2 that are more dedicated to the 13 to 15 years old. The C group, 16 to 18, and we have teachers for the primary school.
Luisa,
Yes?
I lost the connection for a moment. There is a question from Stavrola saying, I'm not in any working group yet. Can I join this one? I'm a primary school teacher.
From Daniela. So,
No, it's from Stavrola.
Oh, Stavrola. I think let me, okay. I'm just reading the messages, I'm sorry. So, okay, Carmen, thank you. I'm not in primary school. So, Stavrola, I have to, did you register yesterday? No, let me. No, you haven't, but I gave you the link, right? But at this point, yes, I think you can join. We have only 3 primary teachers, so that would be great. Okay. Did I miss any question?
I don't think so.
Oh, Daniela, is she here? Oh, how do you recognize it's Venus? It could be Mercury or not, and why? The size. Mercury is much smaller than Venus. I don't know if Danielle is still here. So.
Yes, she's still here.
Okay. So we'll just take a little bit of time to talk a little bit how we are going to work. Let me also put here what we have called office hours. So the idea is that you are going to work with your groups and you are going to produce educational material. You have been put together with teachers of the same age group so that you can exchange ideas and come up with nice collaborative work. You've probably already been assigned to a Google slide that is shared between the group. Of course, the new members not, but they will be added there. And the idea is exactly to produce in that Google slide your own materials. I'm not sure, we still have Joanne here. Joanne.
I don't see anyone with that name here, Luisa.
But she was here. She was here, Joanne Dempsey. So she has left because she could show how the slide was organized. But we can do that also maybe later because I think we have been here already for quite some time. What I would like you to understand is that you have to collaborate with your own group. I'm going to send an email right after this session where I give the contacts of each other so you can contact and I don't know, by email first, and then you can see if you want to talk by Skype or whatever means you want. But there are some hours that we are offering the Zoom. It will be the same Zoom link as we have been using for this week, where I will also be there. So, for instance, today from 3 to 4, if you join this link, we can meet together and talk a little bit on about how we are going to organize ourselves. We can also have a practical session of Salsa J, and you can meet face to face in Zoom with your group. What we will do during this office hours will depend a lot on what you want to do. The first thing that you should try to see with your group is from the demonstrators that you have seen, which topic would you like to explore and take it to your classroom? See if you agree with your partners in the group, so that you can focus in one of the topics that we have talked about. Then we should probably talk and see how you want to organize your work. The idea is to have an activity inspired from the inspired on the demonstrator, and that it will that you know that you can apply it in the classroom, so that it is going to be useful. You're going to adapt it to what you want, and for that you can have the help of other teachers that are teaching the same grades. I know that there are some differences in the curriculums from country to country, but there are also many things that are common. So with a little bit of imagination and courage, we can work together and have something that is adaptable to the different countries and even the different subjects. I see that people are, yes, these are CET time, exactly. Oh, Giulia, you have here the slides. Could you do that? And we won't go very in depth, but it's easier to show what we want. Let me stop sharing.
Yes, sorry.
I will send the working group these hours, these office hours, okay?
Luisa, you have two emails, the email of Stavrola and Janice de Fatima here on the chat.
Oh, messages?
It's yeah, in the chat you have their emails to be included.
So here you.
Oh, here it is. Okay, so this is a Google slide. Probably all of you have already used it, but even if you haven't, it's very, very user-friendly. It's very easy to use it. You will have, for each group, you will have access to edit it. So be careful, do not remove anything so that the other teachers don't get angry with you, but you can all edit. The idea is that you produce this slide show that has the activity you are preparing. And so we have an overview of the lesson pack. It's a little bit like the one page that we showed you of the demonstrator. the name of the activity, the topics introduced, and for the countries that are represented in your group, you can put the curriculum connections that you can see that you can make with this activity. You can identify the reference demonstrator, the age of the students, and how much time you think your activity is going to last. So what type of activity is it? Is it a hands-on? Is it something that you do in a lab? Is it something that you do without computers, like handout sheets, something like that? So that should characterize the type of activity. And then you can describe what the teacher has to do, what the student has to do in this prepared educational resource. The equipment requirements and prior knowledge for students. So this is very similar to that one page that we have for the demonstrators.
I think this was one example, I suppose.
Yes, but the example also had the other parts already.
I'm sorry, I will get, I'm sorry. I think maybe this was then group A.
Sorry. It would be the same thing. Because after that, it's just
no.
Okay. Yeah.
No,
okay. So background and overview of the demonstrator. It doesn't have to say discovering alien worlds demonstrator. It's background and overview, and that's it, of your activity, where you can make a summary of what your activity is about. Okay. So that should be like a summary of your activity, and then you should start the presentation for students. Things that you need to tell the teachers what is going to be done can be added in the speaker notes. See, down there, you say what you want to the teachers that are going to look at this activity that you are preparing. Anyway, when we get back, I'll show you one that has already some parts filled in so that you can get a better idea. But as you see, it's nothing really very complicated what we are asking, not in terms of the slideshow. Of course, the part of the imagination and your adaptation of the resource, that's something else. That might be a little bit more challenging, but that's why we like to have you here, and we like to have you co-working so that the ideas can come and help everyone to take these topics to the classroom. Thank you, Giulia. I think this was just like an overview so that people get the idea of what they have to do. So after I send you the email, between the groups, someone should take an initiative to try to contact each other and try to know each other a little bit so that you can understand what you would like to do. Of course, this was just now. You probably have to think a little bit of about what you have seen and see how you would like to really work on, what you would really like to do. And we will be always in those office hours that I will also send you by email. As for the Salsa J, we will use those sessions. You don't have to go to all sessions. Of course, the more you go, the better it is to collaborate and ask questions. If you want to meet in the group during those sessions, I can break Zoom in a working group and you can talk only between yourselves. If there are general things like Salsa J, we can all work together. So that's the idea of these office hours is to make us available to your doubts and your suggestions and discussions. Am I missing something, Rosa, Giulia?
I think you covered it all, Luisa.
Mm-hmm. Emmanuel?
Me?
Yeah, Manolis, am I missing something important?
I don't think so.
No?
Yes, you, as we wrote, you will all receive an email within the day with all the links to the presentations and the relevant content with
That's another email, okay?
yes, with all the emails of your working group here in order to be able to communicate with each other as well as with the office hours. Also, you have gotten, I think all of you, an email with a short questionnaire in which we kindly ask you to help us evaluate, let's say, our modules to become better and to offer you better training and support. So if you could, please take some time to fill it. I think that this is it.
Mm-hmm. Okay, so any questions from participants?
There is another request, I think, to be included in a group.
Yes, I answered, but I answered only to Manolis. Sorry. And yes, I will. So that's going to be, let me just, okay, that will be done. So I think we can end this session now. And for those that are in the working groups, if you can, we'll be online in the Zoom link at 3 CET. Okay?
Thank you.
Bye.
Bye, everyone.
Everyone.